So our next speaker, Chris, I've known for a long time. I've been in the CSS working group for 12-ish years, been involved with it a few years longer than that. Chris has been in, well, at least the W3C for 25 years. He was... Woo! He was the first chair of the CSS working group. He's been on... Hold applause to the end, please. And he's been involved in so much of the foundational specs that you know and love today. In fact, just recently, Chris can now call himself an Emmy Award-winning specification author for his work on web fonts, the original font specification and the WAF1 and WAF2 specifications. So you should have brought it to show off. It would have been very cool. And like I mentioned before, Leia's working on the color spec, which I very much appreciate them doing better on. Chris is also doing this, and that's what his talk today is all about. So please give it up for Chris Lilley.
There was a comment in Twitter. Someone said that the talks have been quite uplifting, this conference. I have to admit that about 5 or 6 years ago, I gave a talk about the subject of CSS Color, which I entitled 20 Years of Pain, and involved me slitting my wrists on stage. But things have improved since then, so yes, let's keep it upbeat. So that's me, as you know, and that's what I do. Liaison to the International Color Consortium, not the International Criminal Court, just in case there was any confusion. So, topics. We're going to look at color. Color science is a topic on which I could lecture for many hours, and we don't have those hours, so I'm going to do it in 2 minutes instead. Then about the prison of the title of this talk. We're going to talk about how to escape prison in various ways. Whether you can use it. Everyone wants to know whether you can use it. And then lastly, if we have some time, I'd like to talk about high dynamic range as well. And if we don't, that's fine, because no one implements it yet. So what is color? What is it actually? Sometimes people think, well, it's the amount of red and green and blue, isn't it? And you've got 3 sliders and that's a color. What does it mean? I don't know. And some people, you talk colloquially about color. You know when something is bright and zinging, you know when it's muted and this sort of thing. So let's look at what do we actually need from color to talk about it. Well, first of all, light and dark. We need to know whether something's light or dark. So there's a scale. It gives us light and dark. This is luminance. This is the measured intensity of a color. If you've got 2 lights that are the same, you switch one on, you measure its luminance, and then you switch the other one on, your measurement will be exactly twice your first one. So great. Where's the mid-gray, though? It's not in the middle. It's off at one edge. This is not a good measurement of lightness. This, on the other hand, has mid-gray exactly in the middle, and that's what we want. So this is an important concept of equal spacing. A shift this much should be the same as a shift this much over here. You should be able to reason logic with these measurements. So that's what we want from a lightness. Color science has a lot of experimental stuff, and we're now going to do an experiment. So what I want you to do is look at that slide, look at the dot in the middle, for about a minute, and I will tell you. Don't start looking around or you won't see the effect. Just look at it. Halfway there. Keep going. It's worth it, honestly. And tell me what color the circle is. That's a white screen. Okay, we'll do it again. Have you ever noticed if you've got red, you can have a yellowish red, like orange, you can have a purplish red. You can't have a greenish red. It's not possible. You can't visualize that color. Ever think of that? What we have here is opponent colors. Our human visual system actually has this concept built in, literally wired into it, the idea of opposing colors, and you cannot be on both sides of this at once. A color has to be one side or the other side. And there are two sets of them. So we have effectively two chromatic axes. So let's use this as the basis of our color system. We've got a central neutral axis, black here, white here. And then we've got two axes like that, and that gives us a color model. And if the changes in color from one place to the next correspond to how far apart they are, then it's a good color model. If we've got two things called A and B, that's not really very helpful. What we really want to do is take the distance out from the middle. That's the colorfulness, the chroma, and also the hue. We've got a hue wheel. We're going around angular measurement, and that tells us what actual color we're looking at. And the further we get out, the more saturated, the more vivid it is. At this point, some of you are probably thinking, we already got that, Chris. It's got HSL. That's got a hue wheel. It does have a hue wheel. That's all it has. If you take two colors that are 30 degrees apart, they can be radically different, or they can be slightly different. If you look at blue and yellow, they're the same lightness. So HSL, rubbish. On the other hand, any manipulation you do in HSL, you won't go out of gamut, whereas the things I'm going to tell you about are much better and precise, and you can go out of gamut super easily, and then you've got a problem. Go. Now, we've just built a 3D color model. All right, well, it is 3D. There we are. This is the range of available colors on a monitor. Know that it's not a nice even hexagon like HSL, whatever. It's a very irregular shape. Also, the colors change depending on the angle the light hits it. And in general, plotting in 3 dimensions is hard, so I'm not going to do that anymore. Instead, I'm going to look at another color model that's less perceptually even, but easier to use and easier to put on diagrams. Okay, so this is a chromaticity diagram. Round the edge, we have the colors of a spectrum. If you were to look at a laser of one wavelength, or if you're in a very dark room, look at a rainbow, that is the brightest color you can see. Each color is one wavelength only, all of the energy in one wavelength. We can't see beyond that. Any colors outside that don't actually exist. They don't correspond to real colors. And the straight line at the bottom is because there isn't actually purple in the rainbow. It's made by blue and red mixing together in various proportions. And the nice thing about this diagram is that if you have two colors, all the colors that it will mix are going to lie on a straight line. It's not true in other color spaces. So it's very handy. But you can't assume that a shift of this much is the same as a shift this much over here. No. It's kind of squished, and it's not actually very perceptually uniform. And I would love to tell you about why it isn't, but we don't have time. So the prison, you are all mostly in prison. Leah mentioned the HTTP archive search, and one of the things we do is to see how many colors are outside the sRGB gamut. And last time we looked, there were so few, I was able to look at each individual style sheet of the 10 million sites that we looked at, look at them one by one, and see where the colors are and plot them on a diagram, because that's how many there were. There were like 13 websites in the world using them. So I'm going to talk about various broadcast standards as well, and here's the first one, something called Rec 709. It defines high-definition television. It was kind of unique because previously there was one standard in the US and different standard in Europe and blah, 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 and analog TV. And this was for digital HD TV. He picked a D65 white, which is a nice sort of daylight-looking white. And it didn't have a very wide gamut. It corresponded to the sort of TVs that people had at the time, the sort of cathode ray tubes that everyone was using in those days. And from that, there was a thing called sRGB, which differs. It's display referred. In other words, it describes what you're supposed to see when you look at a proper monitor in a studio, what colors it's supposed to have. And it also has a different gamma, because TVs, you look at TVs in dark rooms, right? In your office or whatever, you don't look in a dark room. You have a normal viewing environment, and that does affect. If I would ignore the slides, what color is that corner? There's a black edge and there's a corner. If I just asked you that, what color is it? It's like white or light gray, right? It's also black, because in the context of this, it's a black background. That's the influence of viewing environment, which crushes down the available range of colors. So this defined a certain amount of viewing flare. And there it is. Remember I said that straight lines join all the colors you have by mixing? So I've just literally a gamut as a triangle in this rather than some weird curvy shape. The curvy shape's more accurate, but this is handy. So there we are. There's the primaries and secondaries of sRGB. You can see there's a lot of space that's not covered. Remember I told you can't judge exactly, but still, there's a lot of space that it doesn't cover. But that was actually quite useful because we were restricted to 8 bits. Everything was 0 to 255. And if you have a wide gamut space, you're going to see banding at that, right? So it was actually a reasonable choice. So here we are. I'm talking about color on the web. You'll use color. There's lots of different ways of writing it. What's the problem? Well, that's the problem. They're all inside that triangle. They have to be, because all of those colors, when you actually do a computed style, you get an RGB triple, and that is in sRGB. This is the state of web development from around 1994 to about 2016. Nothing happened. Meanwhile, off the web, other things were happening. This is a cinema. And at one point, films were projected off a big reel of actual physical film. And then they shifted to digital presentations so they don't have to ship around celluloid physically. And they came up with a standard called Projector 3. I assume that there had been a failed Projector 1 and Projector 2, but the Digital Cinema Initiative produced this DCI P3. It specified some slightly weird things, like the white was kind of green, and the total light wasn't very high. It was 48 candelas, which is pretty dim. But remember, you're sitting in pitch dark, so it's fine. Why would we care what they did in the cinema? Oh, yes, there it is. You can notice it's bigger than sRGB. And it has a weird white, as we can see. Well, people started to refer to it quite a bit. Other specifications for consumer electronics. Ultra HD required that you can support at least 90% of that gamut, of that range of colors. Display HDR has a range of specifications of various qualities, but all of them, apart from the really crappy one, don't ever buy an HDR 400, by the way. That's like when they rebranded USB and said that the slowest one was still okay. It wasn't. So it also required you to display at least 90% of the gamut. But the most important thing that happened was Apple took Display P3, liked the primaries, took the sRGB standard, changed the primaries and said, we have a new thing called Display P3. That's why it's called P3, right, from the digital projectors. Well, that in itself wouldn't have been great, but they then went around and produced all of their monitors and all of their laptops and all of their phones and all of their watches all have a Display P3 screen. And they're all measured in the factory, and you have an actual ICC profile for them. And other manufacturers as well, Samsungs and Dells and whatever, started to do the same thing, or with more sporadic success. So basically, this became very important, a very good thing. And if you were writing a native application or doing something like that, oh yes, there it is, again, just to show you that it's the same, then the world was a very colorful and bright place, and you had all these more saturated, higher chroma colors that you could use. About 50% of the colors by gamut volume are outside the sRGB space. So you've got 50% more is what I'm saying. Except if you're working on web development, where, as I pointed out, they're all stuck inside this sRGB prison. And the world is a less colorful place. Welcome to web development. So, how do we get out? See how rapidly I went to the upbeat part of the story? Well, just like this, we have a color function. And you can say display P3 and then give it some numbers which are in a 0 to 1 range like everyone else uses. We don't use 0 to 255 anymore, partly because people could use 10 bits or 12 bits or float or whatever. So we have a 0 to 1 range. We also got rid of commas because Tab wanted to get rid of commas. Sorry, Tab, I know that's not the reason. Oh, and you can do things like that as well. You can put a slash and have the alpha at the end. So there we are. Great. So let's look at that color, shall we, on a chromaticity diagram. Oh, and there's a minimum precision of 10 bits, by the way. You can specify RGB colors using percents, right, and any amount of decibels you want. And if you stuff that into the browser and then query the thing back, you get it rounded to 8 bits. So we said, stop doing that. At least give us 10. So there it is, that blue. Oh wait, it's still inside sRGB. Of course, you can still display white and pale colors and whatever. You can still have all of that. So that one I picked to be inside the sRGB gamut because I don't know what projector I'm going to be using. It's probably like at best sRGB. So I picked that one deliberately. Let's do this one again, shall we? Okay, there we are. We've got primary green, and I've got a nice magenta thing around it to remind me this is an out of gamut color. It can't be displayed on the screen, not correctly. Well, on this one it can actually, but. So it's inside the display P3 gamut, but outside the sRGB gamut. Which means that we'll have to use gamut mapping to actually display it. Sometimes people ask me this, how do I display out of gamut colors? It's like, how do I make my car go faster than its maximum speed? SOL, dude. Okay, oh, look, we've got some values greater than 1 and some negative numbers. I also got a question about this. Is it sucking light out of the atmosphere? No, it's a mathematical formulation. I can do algebra with it, even though it has negative numbers. We've been using them for thousands of years, don't worry. And here's another one. Let's look at these on a chromaticity diagram again. The green one, the purple one, and the orange one. Yes, you can do that. Yes, this is valid syntax. It's not just for this. You can actually do that. So the green one, there it is, right at the corner of the triangle. This is just inside the gamut of P3. The purple one, it's outside. It's still a visible color, but you can't display it even on a P3 monitor. The orange one, we're outside the spectral locus. It's an imaginary color. It's a color that no possible physical device could ever display. You can still do math with it, though. You can still. There's a thing called ProPhoto, which is used for like photo manipulation, whatever. And 2 of its 3 primaries are outside the spectral locus. They're imaginary colors, but that's fine. We can still do math with them. We will talk about gamut mapping, which I've mentioned 3 times already, later. Promise. The link is to, if you want to just click on that link, you can go there now, but if you don't have these slides in front of you, then you can't. So, predefined color spaces in color 4. Well, we've already mentioned P3. I already just mentioned ProPhoto. It tends to get used in some Adobe products and things like that. It's quite good for image manipulation. Rec 2020, I will also tell you about later. It's used for 4K and 8K televisions, and it's even wider gamut than display P3, and I'll talk about it later. Okay, LCH. There's an LCH and an OKLCH, and I'm sorry, that's just the way it turned out historically. And I will tell you more about that, but I don't want to get into it too much earlier on. LCH means lightness, chroma, and hue. So it's the same polar thing we developed right at the beginning of the talk, the good one that you want. You've got 3 parameters controlling your color, and all of them actually mean something. Like chroma is how colorful it is. Hue is what actual hue it is. So the OKLCH and CIELCH, there we are. Also, if you're looking at these slides, I will put, the slides are online, I'm not just trolling you. There's a color space converter that Leah and I wrote where you can convert any one of those into all of the others. And it's what I use to make these slides and to make demos and whatever. It's kind of handy. So we can't go using this stuff willy-nilly. Of course, we have to check whether it's supported, and here's a couple of ways. Firstly, there's an at-media color gamut. Color gamut has 3 values, which in retrospect we should have called normal, wide, and really wide. One of them is called P3. It does not mean that it displays exactly the display P3 gamut. Originally, it was actually the DCI P3 gamut. And really what we mean is if you've got an Adobe RGB screen or anything that's roughly, medium size rather than tiddy sRGB, then that will evaluate to true. And there's also a third value called Rec 2020, which means you're in the future. And these things do exist, but they tend to be like this big and have like 3 lasers and things, and you have to sit here and line everything up and then have your eyes blinded out. So, yeah. And the other thing you want to check is whether the syntax is supported. So, for example, in some browsers, I shouldn't talk about color mix yet, must not talk about that yet, but if you were, that's what you'd want to check for, whether the syntax is supported. Let's step out of CSS for a bit, because Canvas. So CSS, because I said so, has always said since CSS 1 that all the colors are in sRGB. You probably were SOL if you actually wanted to display them accurately, but at least it said what they were meant to be. Canvas, on the other hand, said there's some RGB values, we don't know what they mean. But fairly recently, they changed that, and then you now have 2 options. When you create a canvas, you make a 2D context, you can say you either want a display P3 one, or you want an sRGB one. And everyone uses a display P3 one if it's supported, because if you wanted the other one, you've already got it. And then you can notice you're using exactly the CSS syntax. In backticks, you just stick it in there, and it gets converted to the canvas color space. So there I'm drawing, I've created one, and I'm drawing in 2 different color models to draw on my canvas. Okay, so now we've specified some colors. Let's go on to mixing them. Mixing colors is fun. You can make gradients and make pretty patterns and stuff. So there we are. It's pretty straightforward. Rachel already mentioned this in her talk earlier today. So you say color mix, then you say which color space you want to mix in, because it really makes a big difference. And then you have 2 colors and 2 percentages. And because they have to add to 100, you only have to supply one of them, typically, if you want to. If you supply both, then we'll check that they add to 100. And if they don't, we'll scale them, and etc. But in practice, you say how much you want of one of them, and the other one is computed. So here is an example. We got teal, we convert it to OKLab color space, and it's that. And olive, again, gets that. And then we take the 2 lightness components and we interpolate them in the right percentage level. And then the 2, where are we in? A, B. Yeah, the A and B components, and we interpolate them, and that gives us this result, which we then convert back to whatever we're displaying in, probably RGB. So that's how it works. Oh, the link is to a code pen that does this. So that's the summary. You convert the inputs to the mixing color space. It doesn't matter what they're in, because they get converted. They don't get gamut maps, so if they're out of gamut, you still use these negative and greater than 1 values. They're mixed by the specified percentage, you get a result, and then it might be out of gamut. Okay, let's have a look at a live one. So here I'm mixing lime, an sRGB name color, and an LCH color, and I want 50% of each. And I'm mixing an OKLab, which gets me a nice result. And I can mix in lab, which gets me almost the same result. And I can mix in sRGB, which gives me a too dark result. And I can, let's put that one back to OKLab and change the percentage. And you can see it changing like that. This is based on something that Leah made, and I updated it to show all the workings, because I need that for examples and stuff. So there you can see all the values changing. Like this. Now, if we change to a polar space, like OKLCH, then you'll see that because we're trying to maximize the hue. Instead of going in a straight line, we're going round in a circle. So the intermediate parts have the same high chroma. So again, we can mix it like that. And now let's change something a bit. All right. Let's change that to lab. And if you look, we've got white and a blue, and we've mixed them, and we've got purple. And it's not just a bit purple, it's a lot purple. Discovering this sort of result is why we actually added OKLab, because it has a much better result in that case. See, it stays blue. It just becomes lighter and lighter, as you would imagine, as you're mixing more and more white into it. Okie doke. So that was mixing two colors in a specific percentage to give you one color. But the other context in which we mix colors is gradients. And there is a gradient in LAB, CIE LAB, red to green. Here is the same one in sRGB. Because it's gamma encoded, that means that, and you're doing the result directly on those numbers, you get the wrong answer. Basically, you get them too dark, and there are hue shifts. And this is what all gradients on the web do nowadays. But we're changing that, and I'll tell you about that in just a moment. And I did OKLab just to be sure. It's basically the same in this case. Okay, there's CIE Lab with that purple that we noticed. Really quite noticeable. sRGB, better, but too dark in the middle. And OKLab with a very nice progression. That actually looks as you would expect, even on this projector. It goes from blue to a lighter blue to white without any messing around. So basically, CIE Lab in about a 60-degree area, what you would think of as constant hue isn't. It's a bit curved. Its predictions are off. So in general, if you want to do polar stuff, use OKLab. And if you want to do linear stuff, use OK. Sorry, I said that wrong. If you want to do polar stuff, use OKLCH. And if you want to do linear straight line mixing, use OKLab. And those are the best defaults. So how do we do this? Well, we added a new color interpolation method. There's a regular gradient, as you're familiar with. And we just put in OKLab at the beginning of it. And you can pick whichever space you want, and it will mix in that space. Because sometimes one gradient gives you a better result than others, and you get to choose. We don't pick one for you. You get to pick whatever you want. If you're mixing in a polar space, so you're mixing two hues like this, you could go the short way around or the long way around. And we again let you pick which one you want. There we are. I said I want the longer way around. Modifying colors. So this is called relative color syntax. You have a from and then a color, which is typically a variable, because having a hard-coded one doesn't really help you much. And then, so here we're mixing in LCH, and there are three predefined variables that we can use in our calc called L and C and H. And if you're mixing in X, Y, Z, you'll have an X and a Y and a Z. And if you're mixing in an RGB space, you'll have an R and a G and a B. And you can mix them and do whatever you want to your heart's content. There's a couple of more examples. One in X, Y, Z and one in, I'm saying X, Y, Z because I'm British and I don't say Z, and you'll just have to get over it. And one in ProPhoto. So if you're mixing in an RGB space, firstly, what are you thinking? And secondly, think about it some more, because this is gamma encoded values and you're not going to get the results you expect, and there's probably a better color space you should be using. All right, so that's relative color syntax where you decided to modify a color. But as I've mentioned several times now, gamut mapping, you can specify a value and it can actually be out of gamut, or you can mix two or produce a gradient and they're out of gamut and they have to be brought within gamut. Don't worry, you don't have to do that. The browser does it for you. At the end of the day, we want to produce another color which is similar, but it's actually in gamut. So here's an example. We've got the color, this purple here, and you can see it's quite far out, but it's inside the gamut, this irregular shape here. But as we swing it round by changing the hue, then it goes out of gamut, and now we need to bring it in, along that line preferably, until it's actually in gamut. So what we really want to do is have a constant hue reduction. Keep the hue constant, because a change in hue Like if you have a yellow and it becomes kind of reddish or kind of greenish, you really notice that immediately. If it's a little bit lighter, a little bit darker, it's less noticeable. And if you reduce the chroma, and that's a typo, if you reduce the chroma, then okay, it's a little bit more faded, but that's the least noticeable change. And the color space in which you do this matters. And I did a whole talk about this last year, which if you want to follow that, you can find out all about why we picked OKLab and put it in CSS, even though it's really new. It's only like 2 years old. So this is how gamut mapping works. This is a slice of the gamut of some color space or some display. And we have the orange dot, which is the color that we want to display, but it won't fit. It's outside the gamut. So we draw a line to the neutral axis at the same lightness, and then we sort of binary subdivide until we get close to the edge. So here's an example. We're doing it in CIE LCH, and as you can see, there's this weird purpling happening at this particular hue angle. The color you get is not right. It doesn't have the right hue. Even though you're keeping the hue angle constant, it has a poor predictor of hue. And there's OKLCH doing a bang-up job, and that's much better. So that's what we specified. So CSS actually says, if you need gamut mapping, this is how you do it. The absolute worst way to do it is to just truncate all the values, the ones that are negative or greater than 1. That gives you massive hue shifts. You don't want to do that ever. And that's what all the browsers mostly do now. Okay, Rachel also mentioned this one, contrasting colors. You start with a base color and a list, and it finds the most contrasting one. So here's an example. We pick wheat as our color. It could be the text color or the background color, we don't care. And you give a list of other colors you want to use with it, and it picks the best one. It used the Web Content Accessibility Guidelines algorithm, which has been rightly criticized. It tends to give a lot of false positives to false negatives. It was designed when all websites were in light mode, and now there's dark mode, and it turns out it's spectacularly bad at that. So there are issues with using this. But that's what is specified at the moment. You can also give a contrast, a target contrast, and it will then stop evaluating that list as soon as it's met your target. Aha, but you say, what if it goes all the way through the list and it still hasn't met the target? Good question. I'm glad you asked. And in that case, it will give you either white or black, whichever would give you the highest contrast. So let's look at this example, and I'm going to do the working for you. So we calculate the luminance of all the colors, then we plug it into that equation to get the contrast, and we pick the highest one, which is for this reddish orange color. And that's it. It's simple. You could do it yourself with a bit of JavaScript or maybe with calc, maybe, and the sort of hacks that Leah comes up with where we have complete binary logic and everything. But we don't want to have to force you to bend yourself into a hoop like that. So we just have this function. It does it for you. Okay, this is the question, the part where you're all waiting for. Can you actually use this? And the answer is no, not really, but soon. Soon. I have to say, so people tend to dump on Safari as like, the new IE6 and it's terrible and whatever. And as Rachel explained, yeah, they're bad at some things and good at other things, and so are all the other browsers. And in this particular case, there's some developers that really care about this at Apple. And every time we change the spec, they would change their implementation. They've implemented all of the things that I've talked about. And you can get that in not just preview builds, but the release builds of Safari right now. And the other stuff, it's coming. There's odd little bits of green there where Firefox or Chrome has done some stuff, and I know that they're doing more. So normally I wouldn't even bother to give a talk about something with that bad a support matrix because it's like, we can't use this, Chris. Except, as Rachel mentioned, there's this interrupt 2022, and they're all racing to, within 1 year, get the highest scores possible. So that gives me much more confidence because there's nothing to motivate a browser engineer as much as public shaming. And it's their decision. They've got these, you can watch them every day and see the numbers go up and so on. You can also, by the way, write new tests and tag them with interrupt 2020, then watch the scores go down. Not that I would suggest such a thing, but I will note that, for example, color contrast has precisely one test written by Adam, and there's a bunch of others, like there's no test for the WCAG AA, AAA, etc. So we do need more tests in some cases. And that's good, because that means that we'll not just do the easy things, but we'll get everything working, all the things working together. All right. Well, I'm doing better than I thought I would for time. So having told you about what I feel I've been trying to get on the web for many years and is finally succeeding, let's go into new stuff. High dynamic range. Why should I talk about this at all? Well, there's a lot of content out there, like your news and your Netflix and your sports and whatever are all using this BT2100, which I'm going to explain in a minute, which is wide gamut and high dynamic range. Gaming consoles now have HDR as well. TVs have it because people need to actually watch their Netflix on something. And laptops and whatever have a wide gamut screen as well. And they're starting to get HDR so you can watch your stuff on a laptop. Also, it's not just video, it's also still images. There's an image format called AVIF, which was basically developed because they needed to take a screenshot of some HDR content and display it. And that would be kind of nice if it looked similar. So there's that. And on top of this, there is a need for web content because, you know, you pause your film or whatever, you bring up the actor bios, you scroll through them to find who's interesting. And that's typically web content displayed on top of the HDR stuff. So there isn't a huge crying need to have blinding whites and this sort of thing in CSS itself. But there is a need to display some web content without the white becoming some eye-searing monstrosity that will make you wish you hadn't done it. And that's not a theoretical example, by the way. That did happen in the early days. So high dynamic range tends to imply also a wider gamut. So there we are, Rec 2020. That is, it came out in 2012 because it was their estimate of where we would be in 2020. Spoiler, we're not yet. But there we are, it's pretty good. It's used in 4K and 8K content. And you can use it in CSS Color 4 as well. There it is. You can see it's nicely wide. You'll also notice that the primaries are right on the spectral locus, which means they are single wavelength primaries, easily produced with a laser, 3 lasers. Also, it turns out, so there are tiny changes between different people as to how they see colors. You'll notice this if you start arguing with someone and you say, no, that's blue, that's a green. It's a bluish green, but no, it's a greenish blue. This is just tiny changes in the crossover point of 2 cone sensitivities. And the further you are from white and the closer you are to the edge, the more these are exacerbated. So one actual problem with practical implementation of this is that people aren't going to see fully accurate color. They're going to see slight color shifts. So this is an area of active research at the moment. So most content that's displayed like this is actually mastered in P3, in DCI P3. Then it's converted to 2020 for display. Why would you do that, you ask? Because the HDMI cable that you connect doesn't let you put display P3 or DCI P3 along it. You've got these choices, and it's basically sRGB or 2020, which of the two you're using. So they convert it to 2020. See, the web isn't the only place that has really crap standards that are held together with duct tape. So 2100 is the same primaries as 2020, but it's wide, high dynamic range as well. Minimum of 10 or 12 bits per component. And there are 2 ways you can encode this. One of them is called hybrid log gamma. It basically differs on how much headroom do you have above a normal media white up to the blinding whites. So this one it uses 3/4 of the code space for the normal values, standard dynamic range, and the other quarter to give you 2.5 stops of highlights. And it's designed in such a way that you can view the content in a wide range of situations. It was the BBC in Britain that developed it originally, and NKK in Japan. And they were thinking about live broadcast. They were thinking about sports. And the thing about sports is that people watch them in bars in the blazing afternoon sun. So saying, sorry, you have to switch off all the lights, otherwise you won't get the full effect of the dynamic range, will not be appreciated by the beer-swilling people who are watching this content. So that's the way it was organized. PQ, on the other hand, is designed for very large amount of headroom, but you have to watch it in a dark room. And if you don't want to do that, then you have to do some elaborate tone mapping, which is completely unspecified in the relevant standard. It's just do something so it looks similar in this other viewing environment. I kid you not. So the summary of those is basically using brighter displays so you can display them in brighter and brighter rooms, and using brighter displays to get really bright highlights. That's the two. I mean, this is fine if you're in a grading suite and you've got all the time in the world to make your next blockbuster film and you know how people are going to watch it. That's okay. But on the web, I think HLG is a better bet because we really do have a problem with bright viewing environments. I mean, this is a relatively bright viewing environment, and yet it looks like we're half in the dark here. I mean, imagine trying to look at content on your phone outside. So, bringing it back to web development. There is a proposal in the Color and Web Community Group, which I co-chair, to add HDR on Canvas because people want to be able to write games and write content directly to Canvas using HDR. And how it does, there's an experimental implementation in Chrome. It's behind a flag, but you can play with it. So what it does, firstly, it lets you query the headroom on the particular display you're on. If you get a value of 1.0, it means there's no HDR at all. White is white. And if you get a value of 3, then that means the brightest white is 3 times the brightness, and so on. It lets you query the screen gamut, or at least that's the proposal at the moment. I suspect there may be a privacy objection to this because it lets you fingerprint exactly what sort of screen someone's got in terms of what color the primaries are. But it is very useful information. And then you enable HDR. It's not enabled by default because it uses a lot more power, and that's an issue with battery drain on mobile. And then it goes beyond 8 bits because otherwise you'll get banding. So it's like 10-bit, float, half float, that sort of thing. And it adds 3 new color spaces. And you remember the previous Canvas example, we had display P3 or we had sRGB. So it adds sRGB linear. Why? That's where it doesn't have a gamma curve. It's just a straight luminance. And you remember those negative values that I told you about? Some video cards actually use that as their native format. You give them linear sRGB, and you can use negative values and greater than 1 values to produce a wider range of colors. And then the Rec.21 HLG and PQ that I told you about, you can display content directly in that as well. So this is fine for writing your own content to a Canvas element, and it's quite interesting how they do that, so I hope to see that take off. So this is more the future, but I think we will see it in the next few years. And we're done. And there's the link to the slides. If you want the slides, they're online.
So, thanks so much for that, Chris. It was very informative. A lot of detail, but that's how colors work. Yeah.
Yes. Mm-hmm.
So, a few questions, some from the audience, but again, we're going to start with mine because I'm here. You mentioned a lot about how to specify colors for various things, but the colors that already exist in images and videos and whatnot, how well supported are high gamuts there?
Okay, I should have mentioned this. See, not enough detail. Historically, the first thing to break out of the sRGB prison was raster images, which had an embedded ICC profile to say this is Adobe RGB or whatever. So you could get colors that were outside the gamut, but you couldn't match them from CSS. And that was the original motivation for adding these. Otherwise, we could just say, we'll just add display P3 and be done, or add 2020 and be done. But Adobe RGB, we can't call it Adobe RGB in the spec, by the way. We have to call it A98 and not mention Adobe anywhere, but it is the same.
Trademarks are fun. So somebody had a question that I thought was very interesting here. A lot of these are based on originally perceptual measurements, put people in a room and ask them about colors.
Yeah.
How close are our color models to the perceptual limits of human sight?
Good question. The original research for that was done in 1931. So you can imagine how primitive it was. It was using mercury vapor lamps so that different labs could get at least the same colors and use like 3 sliders and this sort of thing. That has been redone, I think in 2006. So there is a slightly better model than the standard model, particularly for the deepest blues. And also in printing, they have to use a different model because they have optical brighteners. So the UV light actually gets converted to regular light, and there's that sort of, fluorescence and that sort of stuff. But in general, it's not bad. In other words, if you do calculations with the new stuff and the old stuff, you'll get different answers, but the differences will not be perceptual to you most of the time.
Yeah. Question about practicality of using some of these new colors in certain situations, particularly if you have a fancy new color background and a fancy new color gradient, and the gradient's partially transparent, and they're overlaid on top of each other. What do you get there?
Okay. So one of the specs that has not been updated yet is compositing. And compositing, A, uses the wrong equation for luminance. B, composites everything in gamma encoded sRGB, so the result is wrong, too dark, etc. And that is, we can't change that because the web has been like that forever since we could ever do compositing. But we will be changing it. There will be an option to use CIE XYZ, which will give you the correct result. Meanwhile, the gradients that are specified now do use pre-multiplied alpha, as it's called, where you take the alpha value and you multiply all the components by that, unless one of the components is called hue, in which case you don't, because, a 50% of red isn't like 50% of the hue angle. The hue stays the same. So this whole pre-multiplying on pre-multiplying, it used to be specified just for sRGB. Now in the spec, it's specified for all possible color spaces. So at least that part, the part that you're putting on front will be correct. And the part you're putting behind is correct, and the way it's composited is wrong, but it will change.
Eventually be correct.
Yes.
Related to that, the color contrast function. That, it's not clear how that might work with transparency. Does it?
No.
Okay.
It doesn't specify that at all. Basically, instead of having a contrast, which you can say is above or below this magical 4.5 level, you get a range of values. And the spec doesn't mention that at all.
Yeah. Okay. Well, thank you so much, Chris.
Wait, there's more. Also on the color contrast, there was a tweet about this. There is a new color contrast model, which is being looked at for WCAG 3. It has had some experimental verification, but not very much. It's quite complicated. It's not clear that it has to be that complicated, but it's also clear that it does a much better job than WCAG 2.1, which fails to predict adequate contrast rather frequently, like 40% of the time frequently. So there is interest in updating that to use the new one, but the new one needs to be a bit more set before we can use it.
All right. Well, thank you so much, Chris.